In this video, we're going to discuss logistic regression. First, let's describe our data set. This is the Ortho-K data set. There were, in this study, axial length change was followed over 5 years, and there were a number of baseline characteristics measured at the beginning, and then axial length was measured at each year. There were 2 lens types, a spherical optical zone, in which that was the original Ortho-K design, and then later it was changed to an aspheric. The lens was aspheric in the optical zone, made for a steeper slope, more ad in the periphery. Here, this graph is a summary of the statistics, the distributions. This is 5-year axial change from baseline in millimeters. You can see it goes from actually a little bit of shortening of the axial length, possibly due to measurement error, but maybe actual shortening, all the way up to 3.9 millimeters. And this is a frequency distribution. The light curve here is the aspheric, and you can see that it was a pretty tight control, not very much growth around that. And then the spheric lenses, on the other hand, it looks like almost there's 2 types of responses. And the black distribution shows at this end there's a lot of overlap with the aspheric and good control. But then there's these patients out here that had relatively poor control. If we plot baseline axial length against axial length change after 5 years, and we have a line of identity, we can see that the open circles are the aspheric lenses, and they had good control. So no matter where you started, there was just a little bit of growth off the line of identity for baseline. And then similarly, there's this very substantial cluster of spheric Ortho-K lenses that did very well. They did as well as the aspheric lenses, and they cluster along the line. And there's almost this different kind of distribution as we see here in this frequency distribution. There's this group of patients that didn't do very well. Their axial length was not controlled. And so they're delimited by these triangles. And so we have defined in this data set 2 types of spheric responders. We call these people poor control, and the little black dots are good control. So our goal with logistic regression is to determine whether what variables can predict good control versus poor control. And so we've switched over to SPSS, and we want to only look at lens type spherical. So we're going to select cases, and we select if lens type equals 0. And so that gives us our lens type 2 of good and poor control. And so we're going to go into analyze regression. Logistic regression, very similar to linear regression, except now our outcome variable is going to be binary. So we use binary logistic. And we're going to select lens type 2. So our type of lens is now the outcome. And the covariates that we're going to look at are E-value and pupil size. These are going to go into our regression equation. The difference between logistic regression and regular multiple linear regression is the dependent variable is a discrete variable. It can only have 2 levels. If you have 3 in there, it won't work. that's a different kind of regression. But for 2, it's this, and it solves it a little bit differently. We solved linear regression with least squares analysis. We're going to solve logistic regression with our maximum likelihood method. So we get a number of things are up. Let's just go down and see what we've got. It tells us we have a total of 191 cases. It's going to call spherical poor controls 1, so positive responses on the independent variables. As independent variables goes up, that increases the predictability of poor control. This table tells us we have 112 good controls and 79 poor. And the first equation that it does, it just does a simple constant. It doesn't really do a regression. It just fits it in and kind of gives you a baseline point at which we're starting from. And if we look over here, the variables that are not in the equation, if you were to do them one at a time, you'd see that both pupil size and e-value are significant. One thing that I failed to mention when we were in Analyze and Regression, Logistic, we went over here to Options, and we selected this Hosmer-Lemeshow goodness of fit test. And this is going to tell us if our data is consistent across the levels. And so it breaks down the predictions, and then it looks at individual chi-squares, and you want this value to be not significant in order to say that it's a good fit. It's kind of an unusual way of doing it, but that's how that works. And so just did it again, same thing. So let's look at our actual equation. So the Hosmer-Lemeshow test comes out as not significant, indicating a good fit. There is no R squared, unfortunately, in logistic regression. A couple people have tried, and this is a couple of weak attempts at trying to do an R squared. It's just not possible to do it. It's not the same type of formula. This -2 log likelihood is actually a distributed, it's our maximum likelihood, but then multiplied by -2 and taking the log of it. And that's a chi-square. That's a very significant chi-square. So we come up here and it gives us this little classification table that, it's kind of useful, but it says, okay, for those lens type 2s that were actually, they were at the 83, well, no, 80, okay. There were, this is 93 of the spherical good controls were predicted to be spherical good controls, and 93 of the spherical good controls were predicted to be poor. And similarly, the spherical poor controls, 18 were predicted to be good, and 61 were predicted to be poor. So the 61 and the 93 are the ones that the equation got right. So overall, it picked out 80% with these two variables, pupil size and eval. Now when you look at this, the equation is pretty much like we saw in regression analysis. We have a B coefficient. We have its standard error. Instead of a t-test, we have this Wald statistic, which is basically the B divided by the standard error and then squared, so it's it's a chi-square distribution. Its value is with 1 degree of freedom. Its p-value is less than 0.001. And this is the exponentiation of the pupil size. So if we take e to the 1.589, we get 4.897. And that means that for every unit increase in pupil size, every millimeter increase in pupil size, your risk of being in the poor control group increases, or the odds ratio is 5 times as great. E value goes the other way, it's negative. So the higher the E value, and this is eccentricity, and it's a 0 is perfectly sphere and a 1 is an oval. So as it gets closer to a sphere, it is more likely to be a poor control group. So rounder eyes with big pupils tend to be poor control in myopia, and more prolate eyes with smaller pupils tend to have good control with those spherical lenses. So what I'd like to do now is find out what is the overall risk of this equation. So we found for the individual coefficients, but what about the individuals? So let's copy this equation and let's go to Excel. Let's start a new spreadsheet. Let's put this down here. And then let's go back to SPSS. And the way you overall look at the overall is that let's calculate example groups from each lens. So let's split the file into lens type, and we're going to compute means for our two variables, pupil size and eccentricity, and we're going to let's see. So if we go into descriptive, analyze and descriptive, we're going to get the means, pupil size and e-value for good controls and poor controls. Let's copy this table into Excel. And let's line up. So we have pupil size, e-value. So that goes straight across there. And so to figure out, we need to solve our regression equation. So our regression equation is just like in linear regression. We have a constant a plus b times x plus b2 times x2. So what's that going to look like? We're going to take the mean pupil size, because we want a representation of the good controls, what an average pupil size would be, and we're going to multiply that times the B coefficient, and then we're going to add the mean E value times its coefficient, and then we're going to add the constant. And so that's our odds ratio. So that's our log odds ratio. So that's the value of the logit. So So here is the equation for what we just did. We added the constant to the b times the pupil size plus b times eccentricity. And notice that that equals the log of p over 1 minus p, the probability of poor control over 1 minus the probability of poor control, and that's the log odds. So to convert that, we will take the exponent of this value and we get 0.2079. So the probability of being in the spherical good control is, the odds ratio is 0.2. And then let's just cheat and copy this. Copy down here. And now we're lined up again, so we'll just copy these two. Paste. And what we just did was we just moved everything down one. And now the odds of being in the spherical poor control group are 2.3. So you can see that we have our model using pupil size and e-value shows a risk of overall risk of 2.3 to be in the poor control and 0.2 to be in the good control. So it actually did a pretty good job in identifying these variables, pupil size and e-value at baseline were able to predict what this response was. So those are two pretty effective variables. So the smaller the dots here, these guys in here tended to have smaller pupil size and more prolate eyes. These guys tended to have larger pupil sizes and more spherical eyes. But if we were to work it out, you can see that since we matched the aspheric and the spheric groups, the aspheric group basically didn't matter what their pupil size was in eccentricity.